literally. Okay, so we're gonna go in detail about the single displacement reaction that we're gonna be doing in the lab, and that has copper. Literally this copper, which is a solid, right? And then we're going to add silver nitrate. This is my silver nitrate. You can see it's in the liquid form, it's not a solid. It's expensive, it's like $100. That's the reason I want to do the lab really little, so I don't use as much. So if you had to say something about the silver nitrate, you will say that this is solid, liquid, gas, aqueous. What would you call it, Grace? Your guess. The silver nitrate, how should I write it for this reaction? It looks like this. It is not a liquid per se because aqueous, and this is a new concept for all of you, it's ions in solution, right? It's kind of like if I have salt or sodium chloride and I put it in water, right? That solution is aqueous. It's an aqueous solution of ions of sodium and chlorine swimming in the water, right? In hydrated shells. You know what I'm talking about? That's what we did in the, when we were drawing hydrated shells, we were drawing those ions in solution. Everybody okay with that? Yes.
What's the silver nitrate?
So in water, it's aqueous. And we're gonna draw the particle diagram to also help us understand that. And then, what type of reaction do you think we are going to make, Lauren? Single, double, single displacement? What's the telltale sign? Zach? Something is by itself. Yeah, something is by itself, so I will have to guess it may be single displacement, right? Will the copper displace the nitrate, or will it displace the silver? The silver. Metals displace metals, non-metals displace non-metals, right? So the copper will displace the silver, and you will end up with copper nitrate. Copper 2 nitrate plus the silver. Silver is not black, but I just like to write it black just to change the color. The silver that we have out, is that a solid, a liquid, or a gas, Kennedy? The silver here. Should I put solid like the copper, or should I put liquid, or should I put gas? What do you think? Solid, yes. And we're gonna look at the particle diagram, and we're gonna be looking through this reaction so that you see that it is, we may wanna actually look at the reaction real quick.
What's the copper nitrate?
The copper nitrate is what we're gonna have out. Let me show you.
Is it a solid? Is it like what
No,
state?
no, that's why I wanna show you, that's why I think this may be important. So we're gonna start with copper. In this case, it's wire. It could be the wire that comes out of this, right? I could actually take the plastic off and just get my copper. We're gonna start with that, and then we're gonna put the silver nitrate. The silver nitrate ions in solution, and the copper starts as a solid. When the copper and the silver are close to each other, they're gonna feel a force, and the copper will give the electrons to the silver will come out of the solution. This doesn't look like your average silver, but it is silver crystals, and they're growing right there in the copper. And when we do the particle diagram, it'll make more sense. When the copper goes into the solution, it will look blue. So keep this in mind as we're talking through this whole thing. So if you keep this visual in mind, which is what we're gonna do in the lab, in a much, much smaller scale, this will help you see what's going on.
So is it
Aqueous, yes. Because Well, you start is, so let me start drawing it so that it makes more sense. How do I draw the copper? How do I draw metals, any metals in this class? As what? They have a sea of electron and they have the atoms are they big or small when they're neutral? Big. So normally big. And you're right, they do have. So I'm assuming this is my wire that has copper. Is it copper positive or is this copper neutral? Neutral. Is it stable or is it slightly unstable? Unstable, that's counterintuitive. Anything in the periodic table wants to either lose or gain electrons, right? The only stable things are the diatomic and the noble gases. So I have my copper. If you want to be a little bit better about it, although this is not what I'm trying to test here, you'll put your sea of electrons. Sometimes we put a plus in the center just to indicate that it's usually the nucleuses, positive nucleuses surrounded by a sea of electrons. Then in the other one, you can draw a container like this, or what we normally draw just to make it simpler is we draw a beaker, right? This beaker is going to have a water line, and then I'm going to have my silver and my nitrate ions in the solution. So silver is going to be big or small? What do you think? This is an ion. Small because it lost the valence electrons, right? So it's small Ag plus. And the nitrate is going to be bigger. NO3 minus, that's the one that has the extra electrons. Right? And how do I know how many to draw if I want to be more accurate in what I draw? We need to balance our equation to see about what is the ratio of one to the other, right? So that's what I wanted to talk about. Yes, the NO3s, the polyatomic ions, have to be counted as one thing. Don't try to separate it. You can, but better not to. So the first thing I say is I have one copper. Don't worry about it. Silvers, don't worry about it. My NO3s, you're right. You have to add a 2. And this 2 is going to tackle the Ag, or it's going to be a distributive property, and the NO3 as well. So how many oxygens do I have, Harrison?
6.
Yes, you have 6 oxygens. So that's important to keep in mind that it does both. So I need to have 2. I'm going to put another Ag over here. And I'm going to put another NO3 over here. Now, I want to be better in my sketch this time. And I'm going to go ahead and draw the hydrated shells. What side of the water is facing my silver when it's making these little bubbles? Thing. What side of the water faces the positive silver? The most negative or the most positive side? The most negative. Because there's an attraction between positives and negatives. So the negative side is going to be facing, and it's a bubble. Don't draw 2, you need to draw 3 or more. And then here, what side, Kate, is going to surround the nitrate? The hydrogen side. And again, draw 2 or 3. But in reality, it's a hydrated shell. It's a bubble. I'm not going to draw them in here because it just gets to be too much on my drawing, but literally everything is going to be like that. One mistake are several of you going to do on my quiz that I hope you don't. That's why I'm warning you. Some of you are going to see these ions in solution. It's an ionic compound. You're going to put them in solution and you're going to draw them like this. Very common. I see this all the time. Do not do that. They are not together. What you are tasting when you are tasting sodium chloride in water or salty water is ions by themselves, swimming around, surrounded by water. I am tasting the electrolytes. This doesn't happen. This does not exist. There is not an ionic bond here. Tempting to say there is, right? How could I get an ionic bond out of this? If you have salt water, how do you get the salt back? If I have a whole bunch of salt water, how do I get the salt back? Colleen? Evaporating the water, so you take out the water, right? So if I cook it, eventually all the water will go out. You take out the water and you are left with sodium chloride again. So once you get rid of all your hydrated shells, then the positive and negatives will join back and it will look like the original salt and you will have an ionic bond. You will. But right here it's tempting to say that's ionic, and I did mention it will be ionic, but it's only ionic if it's a solid. If it's aqueous, then we're going to talk about another bond that we sort of mentioned before, and we've been trying to creep it in so that we keep remembering what it is, but it's between the water and the ion. There is a bond in there between the water and the ion. What type of bond is this one? Yes. Yes. You're the first one who says it that way. So it's called an interbond because it's like the interstate. It's an interforce, and it's called an ion dipole because water is a dipole. So it's an ion dipole bond. Yes. All of those are ion dipole bonds. There is a covalent bond in here. Can you see where the covalent bond will be? Water has polar covalent bonds, right? That is a polar covalent. Yes. And that's an intra because it's what makes up the water. So it's intra.
So is an ion dipole a type of intrbond?
So there are two types of bonds, right? One is intra, which is what puts my hands and me and all of me together, what puts water together, what puts salt together, what puts sugar together. Those are intra. Inter, how most people like to study them as like interstates, is between two states, so between two things, right? Two different species. So the inters are between the water and the ion. Those are two different things, and it's something that kind of helps them more lightly loose, but still kind of together, right? Making that bubble. The hydrogen bond that we all love to talk about is an interbond because it's between two water molecules, right? Those are inter. Intra is the bond in here between the nitrogen and the three oxygens, which we are not going to draw, but it's obviously not going to look like that in reality. But between the nitrogens and the three oxygens, what type of bond will that be, Bryn? Between nitrogen and oxygen, what type of bond is that? Covalent, right? It's a covalent bond. So it's intra covalent, and it's intra. You don't have to put the polar or non-polar. At this point, I just want you to know, is it inter or intra? And that one within, those are intra bonds. The silver doesn't have it, but that's an intra bond.
So
Yes.
all you talk about ions are
What joins the ion itself, right? What puts the NO3, because NO3 is all it's an intracovalent bond, yes.
So that's what connects the hydrogen to the oxygen?
In the water, yes. So water has two things over here. They will both be connected. If in my head was water and these are my two hydrogens, my oxygen two hydrogens, they will be connected to my head through an intrapolar covalent bond. So let me show you water. Because I do have water.
Is iron dipole the only interbond?
No, we talked about hydrogen bonding. It's another
Can
interbond, right?
covalent and ionic ever be inter? They're always inter.
Intra. Ionic and covalent are always intra. Yes.
Where does hydrogen bonding take place?
Hydrogen bonding takes place. Just a second. Let me show you the water.
So the interbonds connect the water to the That's it.
Okay, let me go back at this. Everybody knows this is water, right? And this is another water molecule. What is the other thing? Okay, what puts water together, right? What puts is an intrabond because it's what makes water, right? That's an intrabond. Everybody okay with that? What puts the polyatomic ion, because that polyatomic ion has one name, that's Anna, right? This is Anna. If something is putting that together, yeah, she's closely bonded to the, once you make the ionic bond, she actually has an attraction to a metal, right? She has an attraction that is going to be more like this, right? And you're going to make a crystal lattice with a whole bunch of Annas and a whole bunch of metals, right? That would be ionic. But what puts something together is always intra. Whereas ionic, whereas covalent carbon dioxide is something similar, right? Just a molecule. So covalent, ionic, and metallic are intra. It puts the metal together, right? That's intra bonds. Everybody okay with intra? Ionic, covalent, metallic. Inter is in between two waters. So this water, the reason that water is how it is, and it is not a gas right now, is because of something that we call hydrogen bonding. And the attraction happens between the positive side of the water and the negative side of the water, right there. And there is an attraction, and it's a very strong attraction, very, very strong. We talked about this before, but let me do it again since some of you have that. So we have my water, and then there is another water. This, you need to tell me which one is more electronegative, which one wants the electrons more, the hydrogen or the oxygen?
Oxygen.
The closer to fluorine, right? So if I were to draw the direction in which electrons are pulled, I will do it like that. And that will make this more negative, and it will make this other side more positive. Right? That's why we call it a dipole. It has two poles. It's a polar molecule, but it has a dipole, right? It has a positive pole and a negative pole. Well, nitrogen, oxygen, and fluorine are the most electronegative of the whole periodic table in that order, right? In that order. So they are crazy, crazy. The attraction is so crazy that this negative is fairly significant. It's slightly, but it's fairly significant because it really draws the other electrons. And this positive is slight, but it's fairly significant. So that attraction is huge. Not like an ionic bond, but it's a big attraction. And that bond that is made right there is called a hydrogen bond. And you recognize a hydrogen bond? You recognize a hydrogen bond because this bond, that's my hydrogen bond, because both atoms that are in both sides have to be N, O, or F. Because N, O, or F will pull the greatest negative and the greatest positive out of that one, right? Because they're so electronegative. Most of the negative is here. This is very significantly negative because this was pulled away. This is very significantly positive. So it's between two N's, O's, or F's. If this were a carbon, would that be hydrogen bonding? Why? Because it may be pulling the electrons a little bit, but not really that significant. That side is not that positive. It's positive, but not enough. So it's not gonna do it. If I had something else in here that was not nitrogen, hydrogen, or oxygen, I mean NO or F, it will not be considered hydrogen bonding, right? It's not. Does that make sense? Yeah, this side of the water is fairly negative. Lots of pull. This side of the water is fairly positive. There'll be other ones that are positive and negative, but not as much as these ones. I mean, these ones are significant. So when you have something that is significantly more positive and more negative, you will have a stronger bond. And hydrogen bonding has its name because it's well known and it's very significant. Okay, we got a little sidetracked with hydrogen bonding, but I didn't want to draw the other water molecule just not to bring it up. But those are inter. Now, let's do a little recap. We have copper, it's a metal. You have a crystal lattice, organized, big atoms, positive nucleus, sea of electrons, right? We have silver nitrate, it's a solution, right? We have silver and nitrate ions all swimming around, not together. They have bubbles of water all around them, every single one of them. They're called electrolytes. Everybody okay with that? The bonding here is called an intrabond, and it's metallic. Metallic, right? And it has a sea of electrons, as Lawrence said. The bonding here, maybe I should have made it green so that it has the same color, but it's a metallic bond. The bonds in here you have, because they're separated, it cannot be called ionic. Please don't put ionic for something that is in the water and separated. And don't put them together either, because they don't belong together. They are separated. So when I have it like that, it is called intra will be within. What makes ANA, right? What makes the nitrates, what makes the ANAs will be within. That's intra covalent. And what's in between two different species, A water and A ion, will be an ion dipole. And that will be inter. Everybody okay with that? Okay. Now, if we are okay, then we're going to do great on the next part, because this part is going to review the other part. I'm going to draw a bigger beaker because I'm going to put my copper and my DAT that I had separated as reactants. I'm going to get a test tube or a beaker, and I'm going to put them together, right? So this is where my products are going to be drawn. In here, I'm going to have my copper, which is going to be small or big? Small, because it's going to be, and I'm not talking about the charge yet, but we did do it at the beginning of class. What's the charge of the copper? 2 plus, right? But it's small. And then I'm going to have the nitrate. And I have 2 nitrates.
Is this like separating the copper like ions?
So what happens is, sorry, I'm thinking about let me put them together first. Thank you for asking, because I got distracted because we didn't finish balancing this, so that kind of threw me off. Let's finish balancing that. What happens in here? What happens to, what else am I missing?
2 silvers.
Yes, so that's what took me out. We didn't finish balancing. So we have 2 silvers in here. So we're gonna have my copper. I'm just gonna put it as I just drop my metal in there, exactly like it is over there.
Why do we have two silvers?
Because you have, when we balance, we have two silvers to start, so we have to have two silvers to finish. We cannot make or destroy anything. So I'm gonna draw my copper, I just put them, and I'm gonna draw my silver nitrate. But I'm gonna go ahead and draw it as the silver is getting close to the copper, because there is gonna be an attraction. Metals always have this attraction, this force between them. This force between them is a force that you know about, but you've never heard it the way I'm going to talk about it. It's an attraction. It's kind of like love between them, literally. It's like magnetism between them, which is kind of like love, right? And it is actually called the electromotive force, but you don't have to call it that. You can just call it voltage. You've heard voltage, 1.5 volt batteries, 3 volt batteries, 6 volts, right? That's what it is. It's an attraction to send. It's a potential energy that is going to send things from one side to the other. But it is sort of like an attraction. And so I'm gonna draw the silvers as they are swimming around and they get close to the copper. The nitrates, I'm gonna draw them. No hydrated shells, I don't care about that anymore, although they're there. And what happens when these two are together, one of these ones is more it wants to get rid of the electrons more than the other. One of these ones is going to be the King Kong of the table, right? King Kong wants to give the bananas to the, no, he doesn't want to give bananas, but one wants to get rid of the electrons more than the other. I couldn't come up with the right example. One of them wants to give the electrons more than the other, right? Boom. So when they get close to each other, which one do you think wants to get rid of them more? Because silver right now is happy. Silver is completely stable. It's an ion in solution. Copper is like this, right? Copper is like, you know what? I need stability in my life, but copper is more reactive than silver is. So the copper, when they're close, is going to go and it's going to lose those two electrons. It doesn't lose one at a time. It has to have the right stoichiometry proportions. When there are two around, it loses the electrons. After that, the electrons will be passed down, right, from one to the other. But you're going to see a crystal of silver start to grow. So when the silver that used to be positive and was all happy, the copper was all unhappy, and the silver was happy. Now the silver won't be happy anymore. What happens to the silver that was positive once it gains the electron? It becomes what? It becomes neutral. If you were positive and then you gain the electron, you become neutral. So you become solid silver. And I'm going to draw it here, although it literally stays stuck over there. But I'm going to draw it here so I don't have a mess. And eventually you could bump it and it will fall to the bottom. So it could literally fall, but you have to bump it because it doesn't just get too heavy that it falls. It starts building a crystal right there. And the electrons are getting passed down and the silver starts being built in there. Yes?
How does it become solid?
Because once you are neutral, you're solid. All of those elements have the same amount of electrons and protons, right? As soon as you get the exact same amount, you become a solid. If you lose one, like copper did, actually copper lost two, you cannot lose two unless you are giving them to someone. In this case, he gave them to the silver, and now the copper, who was unhappy, became a happy copper. And it so happens that the copper ions, well, just one, the copper ion is blue, so you will be able to see a color change in the water. Once those coppers jump in the water, you will see that the water turns blue. Yes?
If, like, you become a solid or neutral, why are the gases gases?
Well, that was something that I said wrong. you become whatever state of matter you are, right? At that temperature and pressure. So the solids will be solids, the liquids will be liquids, but great question. Yeah, I misspoke. And the gases will be gases when they're neutral. Yeah. It's whatever you will be, as they say, like God made you, yes.
So the silver builds a lattice?
It starts building a crystal. It starts building, you know when copper makes the metal? It builds this crystalline structure.
And that's where it gets the electrons from copper.
It gets the electrons from copper, it becomes neutral, and it starts building like crystals do. They start building, and you'll see those crystals grow. They'll start growing. All the electrons will be transferred to all the silvers. The copper will continue transferring because silver and copper are metals, right? So they conduct the electrons really well, right? So the energy is going to be passed down, and the crystals will continue to grow and grow and grow and grow. And that's what you saw in that little GIF, is the crystal was growing because the electrons were being passed down to those silvers, and the coppers were going into solution. Coppers were just like, yes.
What is the bond between silver and copper? Is that inter?
There is a bond doesn't happen here.
Oh.
You just give the electrons, the copper jumps in, and the silver falls down.
Oh, okay.
So copper just goes in there, and the silver falls down.
So copper's no longer a cell.
No, now it's happy.
Exhausts.
It was like this. It gave the electrons and it jumped into the pool. And now it's 100% happy because it has noble gas configuration. It lost whatever it wanted to get rid of, and now it's stable. This is the most stable way that copper is when it's combined or when it's lost its electrons. So in this case, it lost its electrons and it's all happy. And it is surrounded by water, but at this point I don't want to draw that because it can get quite confusing. But the silver falls down, or literally it doesn't. It starts growing, and you can hit it and it'll fall down. So assume you hit it and it fell down. But the silver starts growing and growing around every copper. So the coppers start losing electrons through the metals, and the silvers start growing because of this electromotive force. It's a positive force that says, I am pushing my electrons into you. Silver can never push the electrons to copper. It's not, doesn't have enough force for that to happen, but copper can always push them to silver. Yes?
Nothing happens to the nitrate.
Nitrate? Good question. They are called the nitrate a spectator ion. It was there before swimming around. It was there after swimming around. So these are called spectator ions.
So they don't really do anything?
No, they don't do anything. Spectator ions are just there. And many times, and this is going to lead us to the next part of this saga, in which we write what actually happened. No, everybody doesn't write the whole reaction. Some chemists will write exactly what happened. Why do I care to have my nitrates in here if they didn't do anything? So some people just take them out because they find it cluttered. Now, I want two people, which I'm going to choose, to come out and explain this. And if you need help from me, you can get help from me. So let's say, is it George? No. Marshall. It is, right? Marshall and Miss Wagespack number 2. I didn't know you two were sisters. You are, right? No? Yeah. Wow. So that's not identical twins. Not at all. So you two come over here. One of you talks about the reactants. The other one is going to talk about the products. And we're all going to take about a 5-minute break while everybody, because I may call somebody else out to come and help out, right? But you should prepare how you're gonna explain this. And wait, before I get it